Okay. So that's actually the problem I left off on last time, and that was the problem we started today, isn't it? Okay. So it haunted your dreams. Of course. Okay, so this right here, what you're going to see is this would be the undoing the aldol on addition if you were to go backwards on this in a retrosynthesis. And this is going to be two of the same groups, isn't it? See that? It's actually just two of the same reactants reacting together. Remember that these typically take place in strong basic conditions. They're very similar to like an elimination reaction, right? Ne2. And so what you would see is that this is the reaction right here, but we'd have two equivalents of this reacting to form that, right? And so what's going to happen is we have the OH here is going to take that hydrogen off. That's going to form that enol ion, right? Or enolate. And that's then going to allow this other carbonyl here that's going to give you the alcohol to attack on that position there, which is that beta position, right? Okay. Anybody have any questions? So this right here is your alpha beta positions. Okay, and that right there is your aldol reaction. So let's talk a bit more about aldol condensations. Right here we have propanol. And again, we're going to do this reaction where we have the alpha beta position. We'll end up with the alcohol on the beta position. If we look closely, this right here is this part right here, right? And then your second one is this one. Can everybody see that okay? Okay. All right. So note, however, we get the beta hydroxyaldehyde here. This can actually then undergo another reaction because we have this fairly resonance stabilized area right here with those free electrons that are available. And so you can actually do a dehydration afterwards, removing water right there. And so this is going to be the aldol condensation, followed by a dehydration to remove the water portion right here across and eliminate it to give you the double bond here. Okay, so notice that that is going to be what's referred to as an alpha-beta unsaturated carbonyl carbon compound. Now, you may notice that this was actually that same one we had sort of started with in our reactions, where we did the direct-indirect substitutions. There you go. Isn't that nice? So you've actually wrapped back around and figured out how to make these. Okay? And this is how you can actually insert those. Note that you do get 93% yield, quite good yield. You will get the E and the Z isomers here, because it can go either way. This one right here has free rotation around those single bonds. Okay, let's look at the mechanism. So again, what you're going to get here is when you made this right here, note that you have a hydrogen there, don't you? And so that's that same alpha hydrogen that can take place in elimination reactions that you did before back in Gen Chem 1. And we've seen a few times now in Gen Chem 2. And so the strong base here is going to attack that acidic hydrogen. You're going to take the electrons into a bond with it and remove that acidic hydrogen, leaving behind some electrons, right? Now that negative charge here is right next to that alcohol, isn't it? And so what you can get is it's actually going to be resonance stabilized, which is what you're seeing here. This is the other resonance structure, which is the double bond on the carbonyl, right? Going into here. Okay. So we're moving the electrons up on here and up to here, and that resonance stabilizes this form. Now, the reaction that's going to take place on this resonance stabilized species is going to be those electrons on that carbanion going into a double bond here, and this is going to allow the OH to leave with a negative charge. Okay. Note that this is going to give you the OH minus again. Note that that does make this a catalyst, doesn't it? Okay. So when you're looking at these, because this has a positive charge here, this mechanism right here is going to be reversible. You're going to have an equilibrium. Okay? And so this can go back and forth. And so if you were to put this in, you could get the reverse, of course. You can finish this reaction off by neutralizing it, in which case it'd be much, much harder to go backwards. Okay? Okay, this right here is referred to as heterolysis, by the way, because you're lysing, breaking, right? The hetero part, the not carbon. Okay? So again, this is going to be basic conditions, dehydration for the beta hydroxyaldehyde. This is actually what's referred to as an E1CB mechanism. It's an elimination, just like you guys may have thought of before. And then it's going to be unimolecular. Right here, it's unimolecular. See that? It leaves on its own. And then it's going to be a conjugate base, because it's the conjugate base that is unimolecular, isn't it? Okay. Can everybody see it okay? And so this is kind of the first hints you're getting that this terminology that we've been building up in you, you can take this terminology a lot further. Okay? And you can actually designate reactions in relatively small spaces by using this, right? You can actually designate like an SN1 reaction, and you can further designate that's going to be a conjugate acid. And yeah. All right, so let's look at some another example here. So for the E1CB mechanism, it's going to take place under basic conditions. Under acidic conditions, this is going to proceed via the E1 mechanism, because what you're going to get here is you would get acidification of this OH group, right? You'd have H2O plus, and then this would leave by itself, right? And so you're going to get a slightly different mechanism. Note that you're going to get an alpha beta unsaturated aldehyde here. You won't get the beta gamma unsaturated aldehyde. So if you remember, you can actually leave here, and then you could have done either direction, right? In this case, this direction, this alpha beta one, is going to be greatly preferred, and that's because of that presence of the carbonyl. All right, so this is going to involve ketones. We did aldehydes before. Now we're going to look at ketones. Okay, they're going to be very, very similar, but there's going to be one important difference for these, and that's that we have a carbon there, don't we? We have an extra carbon attached to the carbon we were attached with the carbonyl, right? So instead of having a hydrogen there, that's a carbon. And so some of the things, some of the reactions are going to be much, much more difficult to perform because you're going to have steric strain, right? So for example, any mechanism where we attack down here is going to be much harder to do, right? Just like your SN2 reactions were. And that's because we'll have the steric strain blocking that side out, won't we? Okay. And so, for example, the OH minus attacking down here, that gave pretty good yields on the aldehydes. They give terrible yields when you're looking at ketone, because it just doesn't have space to attack down here, does it? Okay. And so that's that steric strain right there. Again, the aldol reactions can't take place the exact same way for all the ketones as the aldehydes did, because again, you're going to have that extra carbon blocking that space out. Okay. Aldol addition reactions between ketones tends to form very little product at equilibrium because you have that extra steric strain, so meaning it's much higher energy, right? And so you're going to make very little of it at equilibrium conditions. Now, does that mean it's totally impossible? Never look at it, never think about that, go into research and go, Dr. Clausen said it's impossible. Done. No. Like, you can do equilibrium reactions that have very low yields as long as you can remove one of your species during the process, like doing a distillation during it. You can just continuously collect off the equilibrium. Okay? There's actually a lot of things you could do to use poor equilibriums. we've actually done a reaction like this where we used hydrophobicity to drive the reaction forward, didn't we? Okay? And it should have had miserable yields, right? But we played a trick. So there are many tricks you can play. Just I'm giving you rules that you can use to understand these. So the mechanism for an aldol reaction that involves a ketone is going to look like this. So again, we're going to attack one of the alpha position hydrogens here. Notice that's that same sort of elimination mechanism that we had looked at before. And so it's going to give you your carbanion. It is conjugated as resonance stabilized, and so it is going to actually be stabilized in that position fairly well. The next thing that's going to happen is the exact same as before. So we've generated our carbanion here. That's a pretty good nucleophile, and so it's going to attack that electrophile right there, right? And then that's going to put the electrons in the double bond up onto the alkoxide. Now notice that in this case right here, this is a lot more energy to do that, right? We have to overcome a lot more energy strain here because of that steric hindrance versus the aldehyde, which didn't have that carbon right there, right? Okay. And so this is where your problem is for this reaction. Like you have to overcome this energy barrier. But the next step is the exact same. So what we're going to do then is we'll have the proton transfer step, so we can neutralize that to the alcohol. And that's going to give us the OH minus back, and again, that's regenerated, so that's a catalyst, isn't it? So we got our catalyst back. Okay, anybody get lost here? It's the exact same thing, isn't it? Yeah. Just keep in mind this step right here is like that SN1 reaction when we're fully substituted, right? It's going to be sterically hindered. This is going to be a lot slower than it was before, okay? And a lot energetically less favorable. Okay, and so this is that ethanol for the acetylaldehyde. So this is your enolate anion from the propanol. And notice again, we have the carbanion right here. It's going to attack. That's a nucleophile attacking the electrophile. And we see that same reaction over again, right? And so when that nucleophilic species is generated from a different aldehyde and ketone, the one that is attacked is going to be a crossed aldol reaction. Crossed meaning that they're going to be different, that you have different groups on each side, okay? Now, this can actually come with its own complications to a degree, because you end up with two species that are both reactive to this, right? That could both do both parts of the reaction. And so you can get some mix that you have to purify when you do these. Okay? And that's why it has its own special name here, is because you actually need to understand that, oh, this is not just a normal aldol reaction, right? It's a crossed aldol reaction. You could get mixtures in here. You may have to purify. You're going to have two different groups right there. Okay. All right. So this is another example of a crossed aldol. And so we have here two different aldehydes. We're going to undergo this reaction. And this is the desired product right here. And we will get that in pretty decent yield. But we're also going to get all the other combinations, aren't we? To some degree. Depending on how easily they are to substitute. In this case, there's almost no difference in these structures. And so it's likely you're going to get pretty equal amounts of these. Okay? Unless you play some sort of trick in the system. All right. Can everybody see how you'd end up getting all these undesirable products? Yeah, it's just going to do the same reaction for both these, isn't it? And so you'll attack the hydrogen here and the hydrogen here. And either one can act as the nucleophile, either one can act as the electrophile. So you get every combination thereof. Okay, let's look at some of the formations of multiple products. This is the self-aldol for this one right here. This down here is the self-aldol for the red one. Okay. And then these are the different ones getting the alpha elimination mechanism done to them. So for example, this one had the hydrogen removed and gave us that carbanion, right? When we remove the hydrogen here, we get that carbanion. And so we would have an attack here. This one would give us attack here. Is that clear for everybody? Anybody get confused by the fact there's 4 of them? Yeah, it's the exact same thing. It's just when you have 2 of them, there's then 2 options. That's 2 squared. So you have 4 possible products, right? If you had more options in there, then you would square, right? Okay. And then, so these are going to be some synthetically useful cross-aldol reactions that are actually incredibly useful. And one of them is going to be, for example, the benzaldehyde here. And notice that this one has no alpha hydrogens. So whatever aldol you put it with, that's the one that's going to go. That's the one that's going to form the carbanion to then attack, right? Because no alpha hydrogens here to lose. Can't join the carbon. Can't make the carbanion without alpha hydrogen. Yeah. So, congratulations. You only have one option. You get one product. Okay. The second part of the reaction for these is always the same. We're going to give some sort of acidic species to neutralize it and stop the reaction, right? So we can hit the brakes and get our final product. These are some other ones. So, for example, methanol doesn't have an alpha hydrogen at all because there's no alpha carbon, is there? This one, again, no alpha hydrogen. And again, this one, no alpha hydrogen, right? And so this is one of the tricks you can play to only get one product, is you simply can make it so there is no available alpha hydrogens on one of the reactants. Okay? And there you go. Mm-hmm. So it's the carbanion, right? You generate the carbanion in all of these. Okay. And then what you always, that's the one that we're preventing from happening. So that always attacks the carbonyl. So that's going to attack this carbonyl here and bond to those. What we're doing in each of these cases is making it so these species can never generate the carbanion because they don't have an alpha hydrogen. That'll be the carbon over here hydrogen, right? They don't have the carbon over here hydrogen. Okay. And so the base can only generate the carbanion on this position. That's the only option. And then that carbanion is going to attack that carbonyl right there. Isn't that making more sense? Oh, we're having a dehydration due to the acidic conditions. Yeah. So that's that dehydration portion where we did the aldol reaction, then dehydration. Yeah. Yeah. That's that one right there. And that's the double bond. That answer the question? Yeah. Okay, so predict the product of the reaction shown here, in which propanol is added slowly to a basic solution of formaldehyde. So go ahead and start working this out. What sort of product would we make? Everybody should go ahead and start writing and trying to figure that one out. You may realize that when you guys work these things out, that's usually when you get most of your understanding of it. That is actually very true for all things that you actually have to draw out. That's why the Socratic method is the most effective lecture method that's been found. Think it through. I'm going to give you a minute more. It looks like people are actually Okay, gonna move on pretty soon. But one of the questions I want to ask you, see if you can do some deductive reasoning and critical thinking, is why do we have to add this slowly here? Exactly. Yeah. If we put all this in at the beginning, then this would react here, right? And then we'd be able to self-assemble, wouldn't we? So we're trying to keep the concentration of this down. Okay. Very good. Perfect. Okay. And so your mechanism is going to be that alpha hydrogen getting attacked, right, and forming the carbanion. And so that one that we add slowly, that was on the top of the arrow, right, is going to be the one that the alpha hydrogen gets attacked by the OH minus from your strong base. This is going to leave its electrons on that carbon, generating the carbanion, right? And then that's going to be your nucleophile. That's going to attack the carbonyl. The electron's going to move up onto the oxygen. And then the next part right here would have been giving you the aldol product, right? Okay. So once you have the aldol product, however, that tends to self-disassemble when you're under heat and these conditions, right? And so you may have noticed I set you up in the same sort of reaction conditions, same sort of reaction as we had just talked about right before, right? Where we had loss of water, the dehydration. And so the condensation product is actually the likely one to happen, where you're actually going to get this OH coming back in, right, to attack again. Then that's going to lose you the OH minus, giving you a double bond right here. And that's the condensation product right there. Okay. Everybody get that? Okay. You'll note that that's the same sort of product as we looked at right up here. We did the last condensation one. Okay. So let's look at some LDA and crossed aldol reactions. So there's a second way to carry out the crossed aldol reaction selectively. We can use very strong bases. For example, one of the strong bases you can use is called LDA, and altogether that is lithium diisopropylamide. Okay, and what it is it has that nitrogen there, which is normally a weak base, right? But in this case, we have lithium, which is going to donate electrons and make it a stronger base. Okay. This is going to have to take place in not water, like THF will work, because this is a stronger base than can exist in water. Okay? In water, you can't have a stronger base than OH minus. So what's going to happen here, because LDA is such a strong base, it's actually going to deprotonate the alpha carbon rapidly, quantitatively, and it will also be irreversible. And that's the big difference here. One of the biggest difference. See, that arrow is not double-sided, right? It's actually an irreversible reaction because we have such high energy conditions with this LDA that we can't actually go backwards and regenerate that. Okay? All right. And so that's going to give you essentially 100% of the cyclohexanone, which will be converted to the enolate ion. And so you'll have basically 100% of this converted and ready to attack your other species when you add it. Okay? And so you get very good yields despite the fact that you don't have a lot of other conditions driving this. Okay? So the second carbonyl compound, only one enolate anion is going to be available to react to this. So despite the fact that we actually have a hydrogen position here, we started with these conditions. It's irreversible. So we generate all of this as your nucleophile, right? And then this can't be generated into the nucleophile. And so when this is added, it's just going to get attacked. Okay. That's one of the reasons that it was so important I stressed that this has to be added stoichiometrically. Okay? If we added extra of this, what would happen? Anybody know? This would react when you add it, right? Yeah. So you need to add stoichiometric amounts. Okay, so think of it like this. You generate the anion in this step right here. So we're going to have the carbanion generated, the nucleophile. Then we're going to add the electrophile to it, right? And so we'll just get attack the entire time. The next step is then going to be adding acid to finish it off, so you get the OH. And that's just converting the alkoxide to the OH right here. Finish the reaction off. And that's going to give you 70% yield. Everybody okay with that? What do you notice about the temperature of these conditions, by the way? Yeah, it's quite cold, isn't it? Yeah. It's not quite nitrogen cold, but it's what you would normally do is you'd use like hexane and nitrogen and form a slurry. And that's how you usually get those sort of conditions. You could do it with a very, very powerful freezer. There's negative 80 freezers. They're used to like store biological samples and that sort of thing. But you would have to have a really powerful system to actually do a reaction during that, or a very well insulated system. Typically, nitrogen slurries would be the way to go. Does anybody know how you'd actually get a slurry that's the temperature you want, by the way? Okay. What temperature does an ice bath hold? 0? Why does it hold 0? Freezing point, right? So you can actually just choose something that has the freezing point near where you want it, and then you use nitrogen to freeze it, and then the slurry will hold a temperature around there, right? Yeah. That's how you get those sorts. Okay, let's talk about some of the regioselectivity for the aldol reactions. So here we have methylbutanone, and what we notice here is we have this side that has an extra carbon on it, right? And so see, this one right here is a tertiary carbon, isn't it? This one over here is a primary. So which side would we actually see the majority of this do? So there's actually two different enolate ions form right here that can form. One would be this side, one would be this side, right? And so theoretically, you could actually form different aldol products with the same reactant here, couldn't you? You won't get amazing yields because, again, it's a substituted ketone, right? We have a ketone there instead of an aldehyde. But you'd still get your different aldol products that are possible, don't you? So which one do we decide? So the NaOH is actually going to favor deprotonation on the more substituted carbon side. Okay? And so this one that's the more substituted side is going to favor deprotonation. That's going to give you the carbanion right there, which is then going to attack the carbonyl here and give you this product. That'll give you 72% yield. If you use LDA, however, you're actually going to get a different product. And this is where that same thing we had been talking about with irreversible versus reversible reactions comes into play, isn't it? So with NaOH, this was a reversible reaction, isn't it? Okay, and it's going to be in equilibrium. And so what's the one that favors this? The thermodynamic product, right? In this case down here, LDA is going to be an irreversible reaction. And that means the kinetic product is favored, isn't it? Whatever the faster product is. Okay? And that's actually what you're seeing here. So this is going to be more stable over here. It's going to be faster to attack the more exposed side, isn't it? Yeah. And so this one kinetically favored, this one thermodynamically favored. Reversible reaction, irreversible reaction right here, right? Okay. Did I lose anybody in that? No? Okay. Fantastic. All right, let's talk about some intramolecular aldol reactions. So once you get a long enough chain, usually about 6+, you can actually start forming intramolecular reactions. What does intramolecular mean? within the same molecule. Inter would be between two different molecules, right? Does anybody know intranet versus internet? You've heard the internet before, right? You're all using it probably right now. The intranet is like if you guys ever use the internal stuff in Cumberland, where you have to like be on campus to do it. No, you guys don't have that on your one sign. No, that's fair. That's fair. You might not. So the intranet would be things like if anybody has like a drive at their home that they can drop things when they're at their home. A lot of like AirPlay does that, where it only allows it at home if you have certain security settings. That would be your internal network. Everybody's heard of a firewall before, right? Okay, that's inside your firewall. That's your intranet. That's actually what the firewall is actually referring to. Okay. So intramolecular, we're going to react within the same molecule right here. We've actually seen some examples of this before, but in this case right here, what you'll notice is you can actually take that alpha hydrogen off here, right? Generate a carbanion, and then it can attack over here. The important thing about this is you need to have something large enough that when it wraps back around, it can generate typically a 5-membered to an 8-membered ring. Okay? Anything smaller than that is going to really struggle to wrap back around and actually react. Okay? It's actually impossible once you get below 3-membered rings, right? But 3 and 4-membered rings are very high energy, right? And so it's going to be very difficult to do that. 5-membered rings are fairly low energy. 6-membered rings are very low energy, right? 7-membered rings are also fairly low energy. So, and 8-membered rings are higher energy again. Okay. So again, this is your intramolecular reaction. Right here's the mechanism for it. It's the exact same mechanism as hopefully you already went, oh yeah, same thing over and over. We're going to take the strong base, attack the alpha hydrogen on one side. In this case, it's symmetric, so it doesn't matter. Okay? And then the next step is we attack the carbonyl carbon with that carbanion. We would get this product right here so far. We'll do the proton transfer step to neutralize that to the alcohol. And that would give us this product here. Now, because we're under basic conditions, and there's another hydrogen right here, that will again attack the alpha hydrogen. And this is going to cause your hydrolysis or your dehydration reaction, right? And that's going to give you the double bond right there. Okay. And that's that same reaction as before, right? The only difference now is that it started as one molecule, now it stays as one molecule, right? Okay, so let's look at some other examples. What if we have pentane diol, excuse me. Okay, pentane diol. Is this going to work very well? So if we do this reaction, we would wrap back around and make a 4-membered ring, right? 4-membered rings have a lot of steric strain, don't they? And so what's going to happen is when it tries to wrap around to make that bond, it's going to really struggle to do it. And so you're likely not going to get any product at all. If you did get product, it'd actually be very difficult. Okay? You'd have to really set up some conditions. This right here is going to be the octane diol. And so the 7-membered ring is also not very favorable. You have to really drive that reaction forward. The 5 and 6-membered rings are going to be your most favorable ones where you don't really have to do anything to get them to work. Okay? Your 4 and 7-member rings, they're going to be higher energy. So they're going to really, really struggle to form if they do at all. Likely with NaOH, you're actually not going to be able to do this reaction. Okay? Just under the conditions we had looked at before. Okay, so this is a favored intermolecular reaction, and what sort of reactivity trends would we be looking at here? So note this one, we have a ketone, and we have an aldehyde on the two sides, right? And so this one's going to favor one of those sides, right? Specifically, what we're going to see is we're going to favor an attack typically on this aldehyde position right here, right? Kinetically, at least. Okay. Now, what you'll see here is when we take the hydrogen off of here and give the carbanion on the furthest position here, that's going to make a too big ring, isn't it? Yeah. So the ring's too big. It's going to be disfavored because that ring is too big. It's going to have extra hindrance to it, right? Okay. When we take the electrons off of this, that's going to give a very favored carbanion and aldehyde set. It's also going to give you a 5-membered ring, which is fairly stable. And so that's going to be the favored reaction by a lot in this case. This right here again is going to be, well, this would give you the right ring size, right? But you have to attack into a ketone, don't you? And that's going to be sterically hindered here. And so this is also going to end up being disfavored. Okay? And you're not likely to generate much of that product because you'd have to attack the ketone position, which is a lot more sterically hindered. Okay. Did everybody keep up with that? And anybody get confused here? Fantastic. Okay. Okay, let's talk about the Robinson annulation. So your Robinson annulation reaction is going to be essentially the conjugate addition of an enolate anion, which would be called the Michael reaction. That's actually what that'd be for named reactions wise. That'd be the enolate anion reaction, followed by an intramolecular aldol condensation. So this is what the overall reaction is going to look like. We have this right here, ketone, another ketone that has a double bond next to it. See that conjugated system? Okay. And so we're going to react this conjugated system with this group right here. Notice the replacement here, followed by a connection around, right? Okay. These are the sort of conditions you'd be looking at. KOH with ethanol, 20 degrees Celsius, 12 hours, takes a long time usually, and you'll have to reflux for 1 hour to get it going. Okay. All right, let's look at the mechanism now. So the first part of this is going to be, really the mechanism is just going to be two of the reactions you've already seen put together, okay? We're just combining things that you already know. So we're going to have our strong base, or KOH, OH minus. It's going to attack that alpha position hydrogen. It's going to leave you at the carbanion again, right? So we have the carbanion. What's going to happen next is this is going to be that nucleophilic addition that we'd looked at before. Remember the conjugated nucleophilic addition? Okay. And it's going to be on the conjugated position, right? The 1,4 position. Okay. And so we'll have the nucleophilic addition onto that right there. The electrons in the double bond will shift up into the middle. And then your carbonyl is going to go to that oxide, right? Okay, so the next part right here is going to be a proton transfer and tautomerization step. So it's that same sort of tautomerization. Remember, this is your enolate right there with the proton transfer to finish it off. And so that's where it comes back in, and we put the hydrogen on, right? Okay, so we generated our carbonyl at this position right here. What's going to happen next is this gives us a new alpha position, doesn't it? So we have the alpha position right there. That is going to be the next proton transfer step, i.e., we're starting a new E mechanism around way. So we're going to get that same proton attack again. So the OH is going to take this proton, it's going to generate our carbanion. This carbanion is then going to attack the carbonyl in an intramolecular aldol, right? This is going to be that nucleophilic addition here. That's going to leave us with the alkoxide right here. We're going to get another proton transfer step. That'll give us the alcohol there. And remember what happens to alcohols a lot of times that are near carbonyl alpha hydrogens? Whenever we do these reactions, we kept having those dehydrations, right? And so we're going to have the exact same dehydration again, okay? Where we'd have this alpha position hydrogen getting taken by the OH, the hydroxide comes off, leaves us with the double bond. And that gives us our final product right there. And so note, it's just everything we've learned in this chapter, one after another, right? Yeah. Because they were all related reactions that can happen over and over together, right? Yeah. Okay. Let's consider some considerations for these Robinson annulations. So right here we have an alpha hydrogen. This one here has 2 alpha hydrogens. And this has an alpha beta unsaturated system, this being the alpha beta right here. Okay? So when we look at our final product, what we're going to see here is this double bond here is going to be the one that makes it, the carbonyl here, is going to be the one that ends up making that double bond with the 2 hydrogens right there. And that's actually one of the ways you can tell which side would react. Is because you're going to have 2 spots to make bonds, right? This over here, the alpha beta unsaturated, is going to be what makes the other side here. Okay, so let's look at the aldol and Robinson annulation reactions in your synthesis. So right here we have LDA working. And so your aldol reactions are actually very valuable tools for organic synthesis. And one of the reasons they're so valuable is they're one of the easier ways to form carbon-carbon bonds, right? And so you can form a variety of carbon-carbon bonds, including double bonds. They're going to involve ketones and aldehydes, which are extremely common to find in nature. So you can find lots and lots and lots of reactants all over the place, right? And so you can start with fairly complex structures already that are already mostly what you want, and then just add carbon bonds to those. And notice that the ketone and aldehyde positions are extremely common throughout all sorts of positions when you start looking at biological cycles, right? So these are very easy things to get your hands on. Okay. So you can actually use this to modify structures, existing structures, into almost completely different structures based on these aldol positions, right? You can selectively protect certain positions, so you can target other ones. And then you can wrap it around to make a ring here. You can bind it to each other. You can bind something else. You can make your own rings in it. You can do all sorts of things, right? So at this point, your guys' toolkit is just massive, right? Really, your bigger problem is going to be figuring out what actually makes sense of the tools that you have, right? So, okay. One of the more impressive things for this is the aldol reactions can actually be used to link two very elaborate carbon frameworks, and this is actually the example right here. So in this case right here, we're using LDA to generate our carbanion first, and then we're going to add the other structure here to react, right? And these things are extremely elaborate, aren't they? Like, this is a lot of functional groups. It'd be pretty difficult to name, right? And so is this one. Okay. And we can actually link them up at a very specific position because these are going to very specifically target the carbonyls, right? And specifically, the aldehyde one is going to get targeted, isn't it? And so we can link these up, and we create a very complex structure that if you tried to create from scratch would be nearly impossible, right? Yeah, it'd be massive amounts of work, 30-something steps at least, and good luck actually getting a yield at 30 steps, right? So, kind of a useful thing, right? Yeah. So, one of the big uses for aldol reactions and where you'd actually see them the most, or one of the most reasons, is not actually these small molecules we've been looking at. It's actually as a final step to link up parts of structures. Remember we had talked about synthetic pathways, where you can increase your yields overall in the synthetic pathway by branching your synthetic pathway, right? And that's one of those branching points. Okay, so let's talk a bit more about the retrosyntheses involving the aldol reactions. So when we're going from the retrosynthetic perspective, this right here is going to be your beta hydroxy carbonyl compound. And what you'll see here is you always cut it on the side with the hydroxy, right? Because that's going to be where your alpha-beta connection is, okay? The carbonyl is one of the carbonyls still, right? So you're going to cut it right there. And that would give you the reactants you would have had to use to make it, okay? Now, when you have the double bond in it, because it's undergone the dehydration, you cut it at the double bond, right? So the carbon-carbon double bond is where you cut it. Your reactants that you would have had to make, this double bond gets an oxygen on the other side for this side right here, the beta side. This one right here, which is the alpha carbon, is going to get a hydrogen because you would have had to lose alpha hydrogens, right? Does that make sense? Now remember, for these reactions where you did the dehydrations, you always had to have lost 2 alpha hydrogens, didn't you? Because one was made to make the single bond, the other was made to make the double bond, wasn't it? Okay. And so they're actually kind of easy to draw out the reactants back out. That's one of the kind of nice things about this. So if you ever do these, you can actually really easily do this by just starting to draw this like a really long double bond here. And just copy this as if you're drawing a really long double bond in between. And then you erase the double bond in between. One side gets a carbonyl here. The other side is just going to get hydrogens there, right? So as long as you use a pencil, you can actually do these very easily and not have to think a lot. Okay. So again, these are more examples of these retrosynthetic, figuring out what reactants we had. So this is going to be an on-do aldol condensation again. In this case right here, we see that we're actually attached at another point, right? Not just at one point here. And so these had to have been the same molecule at the beginning because we made a cyclic structure here. Assuming this one reaction, of course. And so our target would end up being, we look over here, there's the carbonyl, right? That has to be the alpha position then. That one's going to get hydrogens on it. This side's going to get a carbonyl on it, right? Everybody keeping up? Okay. Any issues? Questions? Okay. All right. Very good. This is the Robinson annulation for the retrosynthesis. So remember, this is actually going to end up being a series of steps. You can actually subdivide these out as the aldol condensation and Michael addition. Okay? And it's typically helpful to do that because it gets a little confusing when you try to do multiple steps at the same time in a retrosynthesis. Though with practice, you can. So the first thing you're going to want to do is undo the aldol condensation, which would have been the second part of your reaction. And so that's going to involve splitting that alpha-beta double bond. And again, the side that's next to the carbonyl is going to get the hydrogens. The side that's no carbonyl is going to get the carbonyl. Okay, so once you're to this point right here, we're going to undo our Michael addition. Now, the Michael addition is going to be right here. And remember that this is going to involve a conjugated system here, right? So it's going to be an indirect. So you always look for the carbonyl, and then you have to remember you're a 1,4, right? So you go 1, 2, 3, 4. Okay? And that's the carbon where you have to split. And so we split right there. Notice that this right here is going to leave then with this remaining structure. Again, that's going to be that alpha right there. This was your alpha right there that generated your carbanion, right? Okay. And your double bond goes in here to give you your conjugated system. Okay. So in summary, you're always looking for carbonyls. There's two spots that are always going to be important for these steps, right? There's where you generate carbanions, where you have the carbonyl being attacked, right? Okay. So you look for your carbonyl here, and notice it's off one position right here, which is the alpha, right? So that had to have been the carbanion, right? So that will have hydrogens, because you have to take hydrogens off. The other side had to have been where you attacked, wasn't it? And so that has to have a carbonyl so that you can attack there. There's no other carbonyls near it, so it's definitely not an indirect one. All right. The other one, when we look here, again, we look and we see, oh, this is not anything that makes any sense for the alpha position. This one has an alpha position that has something that would have been added to it. So that's your alpha position. That's going to get hydrogen, isn't it? This one right here, well, it's real close to a carbonyl, isn't it? It could be a conjugate system. And so this conjugate system is going to get the 1,4 with the double bond. Okay, let's talk about the ring opening and closing for your monosaccharides. So if we actually were to look at glucose in blood, what we would actually see is about 0.003% of glucose in any water system typically exists as D-glucose in the open chain form. The vast majority of it, 99.8% or better, is going to exist in this closed form right here, which is the hemiacetal form, D-glucopyranose. Note that you do have one other form that it can exist in, which is the D-glucofuranose, which is the 5-membered ring one, right here. That's usually less than 0.2%, but still more than the open chain usually. Okay, it's actually quite a bit more prevalent than the open chain typically. Now note that this is an aldehyde right here, isn't it? This is under water conditions. Typically, you can get this to happen more often at 40 degrees Celsius. You can get more ring opening and closing, and for the exchange to work better. And this is going to generate the hemiacetal right here. Does anybody know what the hemiacetal is versus the acetal? You got it. Exactly right. Yeah, so in this case right here, what we have is we have OR, right? There. And then OH. So that's hemi-half acetal. If this was another R group, like a starch or something like that, that would be acetal. Okay. This will have a mixture of the R and S forms. Which one it will be is dependent on the stability. This right here is the D-ribose, and what we can see is that that's also going to majority exist in the ring closed form and any water system. Okay. It's not doing what I want. All right, so this is actually the mechanism for this reaction. So what you're going to see here is we have the OH group at the end here. By the way, does everybody know DL here? So for sugars, on the right side is always the D. On the left side here would be an L. Okay. Okay. And that's actually why they write these out like this, because it makes figuring out which conformation of the sugar you have much easier. Okay. Remember that this is actually the projection. In reality, this doesn't actually look flat. Okay. These are actually coming out towards you across the horizontal right. The vertical is actually going away from you. Okay. Okay, so what's going to happen here is we're going to have a nucleophilic addition here, and this is going to leave the electrons up here on the oxide. You have plenty of water available in the system, and so you're going to get a proton transfer, which will give you alcohol right there. Your proton here is going to be lost to water, and so that will neutralize your entire structure. Yes, this is a zwitterion, by the way, in case you're wondering. Does anybody have any questions about that? The ring closure. Very similar reaction to ones we would talk about, right? Okay, so this one's going to be the 5-membered ring being formed. And the only difference here is instead of the last OH on that one, it's going to be this one right here. And so that's going to wrap around. That's going to attack that carbonyl there. And we'll just get the exact same for the rest of the reaction. And so we lose a proton from water to neutralize that. We lose a proton from the structure to water to neutralize that portion right there. And that gives us our closed ring form with 5 membered ring. So let's look at the anomeric carbons here. So the anomeric carbons is actually going to depend on which side this OH would end when you do this ring closure. Okay? So if the OH attacks from the top here, what you're going to get is the anomeric OH right here, the anomeric carbon here, is going to be on the bottom like so. Note that this is actually this structure here. It's not, planar. In fact, this right here means that it's down like that, right? And so it's just another way of representing these structures. So it looks easier to find top and bottom, okay? But these are actually the exact same structures. So this is actually in this position here. Okay, everybody see that nice equatorial? Is it equatorial? No, it's axial. Got to test you now. Okay. Now, note that we started with D-glucose, right? So the important thing to look at for the anomeric carbon is to look right here. This is the anomeric carbon. The OH, it's the one next to the oxygen in the ring, right? It has an OH on it. Okay. So if it's pointing the opposite direction of this carbon right here, that's going to be alpha. If it's pointing the same direction, that's going to be beta. And all the beta is when you attack from the bottom instead. That's going to cause this oxygen to go up, and it'll end up on the same side as this one right here. And that's entirely what dictates alpha beta for these anomeric carbons, okay? It's just another isomer that you can have for these sugars. And it's actually quite important when you start looking at things like cellulose, starch. It's actually a lot of why cellulose and starch are different. They have mostly the same structure, actually. But the big difference being they have a different anomeric arrangement. Okay? So you actually get different overall three-dimensional structures. Okay. So this is some of your properties for your anomeric arrangements. Remember again, alpha is opposite sides, beta is same side. Okay? And so they're going to give you slightly different physical properties. For example, your melting points are going to be a little different. 146 for the alpha, 150 for the beta. And so if you're very careful with the melting points, you could actually get a difference. Okay? It's not a huge amount because they are just isomers, right? This right here is the light rotation. Notice this is a plus 112. This is actually just plus 18.67. So the easiest way to tell these is actually to use a polarimeter, right? Because they'll be quite easily separated depending on polarized building. Anybody have any other questions for these? Okay, I'm not going to go super far into, because you guys will all have like biochemistry at some point. But please keep those in mind. They're going to become important in biochemistry, okay? They're already important in biochemistry, but you may not have actually gotten to experience them yet.